All right, let's get right into it. When you get down to it, organic chemistry isn't really about memorizing a million different reactions. It's more about understanding one single fundamental interaction. You can think of it like a dance between two key players that pretty much governs everything that happens.
And this quote just nails it. Almost every single reaction, from the most basic to the wildly complex, it all boils down to this one elegant idea. A molecule with a lot of electrons meets one that doesn't have enough, and something new happens. So let's go ahead and give these two dancers their proper names. We need to understand exactly what roles they play on this chemical stage.
This slide really brings it all down to its simplest form. On a basic level, you have a giver, which is rich in electrons, and you have a taker, which is, well, poor in electrons. The giver donates a pair of electrons, the taker accepts them, and boom, a new bond forms. That's it. That's the entire dance. So, our giver is officially called a nucleophile, and the name tells you everything you need to know, really. Phile comes from the Greek word for loving, so a nucleophile is literally a nucleus lover. It's drawn to the positive charge of an atom's nucleus because it's got this pair of electrons that it's just dying to share.
And on the flip side, our taker is the electrophile. Same logic here, it's an electron lover. It's electron deficient, so it's actively looking for a pair of electrons to make itself more stable. You see, the nucleophile has exactly what the electrophile wants.
Now, if these ideas are ringing a bell, they absolutely should be. A nucleophile, an electron-pair donor, is, by definition, a Lewis base, and an electrophile, an electron-pair acceptor, is a Lewis acid. This isn't just some random coincidence, it's their identity. It connects this core concept of organic chemistry to the much broader idea of acids and bases you've probably already learned about.
Okay, so we've got their names down. Now, how do we actually spot them out in the wild? This next part is going to be like a practical field guide for identifying these chemical players.
For nucleophiles, the rule is super simple. Just follow the electrons. You're basically looking for a spot in a molecule that has this high concentration of electron density. So there are three big signs to look for. First, and most obvious, is a negative charge, like on a hydroxide ion. Can't miss it. Second, look for atoms with lone pairs of electrons, which you'll find on neutral molecules like water or ammonia. And third, the electrons in pi bonds, the ones in double or triple bonds, they're a bit more exposed and can totally act as a nucleophile. Now for electrophiles, you're looking for the exact opposite. You're hunting for an area that is just hungry for electrons, an electron-deficient center. And the checklist for an electrophile is just as clear. A full-on positive charge, like on a carbocation, that's a dead giveaway. But what's more common is seeing a partial positive charge, that little delta plus symbol, on an atom that's bonded to something really electronegative, like the carbon in a carbonyl. And finally, molecules with an incomplete octet, like boron trifluoride, are huge electrophiles because they have an empty orbital just waiting to accept some electrons. Okay, let's put it all together real quick. This table just summarizes their roles perfectly. The nucleophile is electron-rich. It's the one doing the attacking, and it donates electrons. The electrophile is electron-deficient. It's the one being attacked, and it accepts those electrons. Giver and taker. So, now that we can actually identify the players, let's see what happens when they finally meet. We need to learn the visual language that chemists use to describe this dance.
I just love this metaphor. If a reaction is like a carefully choreographed fight scene, then the curved arrow is the script. It tells us every single move. It shows us exactly how the electrons flow, from the attacker to the target.
And the rules for this choreography are incredibly simple, and they are always consistent. The arrow always starts at the source of the electrons, so the nucleophile's lone pair or pi bond. The arrow's head always points to the destination, that electron-poor atom of the electrophile. And that one little arrow shows us precisely where a new bond is about to form. Okay, let's watch a reaction unfold. So on one side, we've got a hydroxide ion, OH-. Notice it's got that negative charge, it's got lone pairs. It's a textbook nucleophile. And it's approaching our other molecule, methyl bromide. Now, because that carbon is bonded to a very electronegative bromine, that carbon atom becomes our electrophilic center. It's the target. And here comes the action. You can just picture it. One curved arrow starts on the hydroxide's electrons and points right at that carbon atom. That's the attack. But wait, carbon can only have 4 bonds. So as this new bond is forming, an old one has to break. A second arrow shows that carbon-bromine bond snapping, and those electrons move right onto the bromine atom. And the choreography is complete. The result of all that electron movement is a brand new carbon-oxygen bond, which creates methanol. And the bromide ion has left, taking those electrons with it. We've just perfectly shown a classic nucleophilic substitution reaction. Okay, for our final section, let's dig into a really common point of confusion. The line between a nucleophile and a base can seem kind of blurry, but understanding the difference is absolutely critical for predicting how reactions will go.
Here it is, the one crucial difference, and it is all about the target. See, both nucleophiles and bases are electron donors. They're both technically Lewis bases. The only thing that separates them is what they decide to attack.
This table here lays out the different job descriptions perfectly. A nucleophile attacks an electrophilic carbon atom, and its strength, its nucleophilicity, is all about how fast it can do that. That's kinetics. A base, on the other hand, only attacks a proton, an H+ ion, and its strength is a matter of equilibrium or thermodynamics. So it's the same action, just a totally different target.
So what makes a molecule choose one job over the other? Well, a lot of the time, it just comes down to physical size, what we call steric hindrance. Think about it. A big, bulky molecule might have a really hard time squeezing through a crowded space to attack a carbon atom buried in a molecule. But a proton, it's tiny, and it's usually sitting right on the outside, making it a super easy target. This is exactly why tert-butoxide, which is a very bulky molecule, is a fantastic base, but a truly terrible nucleophile. It's just too big for the job of attacking carbon. So in the end, it turns out that so much of organic chemistry is really just this one story told over and over again. It's a story of electron givers and electron takers. It's a dance, it's a fight, it's this incredibly fundamental interaction. So the real question is, now that you can spot the players and you can read their moves, what reaction stories are you going to start to see playing out in the world all around you?